Bartosz is a software engineer and consultant with almost 20 years of commercial experience in the digital TV industry. Bartosz is a big fan of the Linux ecosystem and open source in general. He likes to call himself a Linux detective and rarely leaves a bug investigation unsolved. Bartosz has years of experience in C, C++, Linux security, and software integration in embedded systems, seeking an opportunity to pick up some Rust soon. Bartosz is also passionate about knowledge sharing and ran numerous well-received internal trainings and workshops in the companies he used to work for. In his spare time, he likes to make a wine and maintain a home lab for running a number of self-hosted services for both of the advantage of himself and the family. So without further ado, I give you Bartosz Moczulski, Shadow Stack, Fixed Memory Corruptions, Immune to Stack Protector. Big round of applause.
I was about to start with something different, but after attending the keynote in the morning, the keynote from Hepsata, I cannot underestimate how much my presentation will relate to what he was talking about. If you've been there, he was mentioning security very much, so what I'm about to show you is very much relevant. Right. Encounter, embrace, and eliminate. That's the standard recipe for bug fixing. That's how we go about it. And of course, you first need to learn about the very existence of an issue. Maybe you spot it yourself, maybe your teammate reports it, maybe it comes from your tester, maybe it's reported by your customer, the users of your application. That's usually the worst scenario, and it just pops up in your Jira or whatever other bug tracking system you use. Once you know it, you need to start analyzing it. You gather some evidence, maybe you gather the logs, maybe gather code dumps, maybe try to replicate it on your own desk, whatever is necessary. And after you've done your analysis, you probably will have already a good understanding what's wrong and how to fix it, hopefully. And yeah, by that time, you start preparing your bug fix. And that's roughly how my talk today is going to be structured. You will see it in the next slides. Just to make sure that you made it to the right room, I want to ask you, how many of you had to deal with memory corruption issues before? All right. Oh, God. It's almost entire crowd. I'm glad. And perhaps specifically stack corruption issues. Still quite a number. I'm impressed. Yes, so I was doing it myself for the last 2 decades or so. Not just memory corruption, also other types of issues, multi-threading issues, integration issues where things used to fit together, but they no longer fit together after an upgrade, or perhaps just no longer fit together because of other reasons. You know, logic errors, resource leakage. Hepsata was referring to that as well. That's why I like to call myself a software detective, because I spent, frankly, majority of my time, my professional time, investigating bugs, not necessarily writing new code. And I think that writing new code from scratch is easier. Writing or creating a new programming language from scratch is way easier than making an existing language better and improving it. If you've been living in one of these areas of the world, you might have come across the products that I helped develop across my career. These products are usually set-top boxes. If you don't know the term, these are the small router form things that you put next to your TV. You connect it to your TV in order to be able to receive your satellite television, your cable television, or maybe terrestrial television. So if I can ask you for one thing, it would be to keep watching TV, because it gets me keep my job, which I like very much. And just to clarify, I'm about to talk about stack. And let's just tell which type of stack I will be talking about. It's not the stud stack from the C++ standard library, although this is interesting all in itself. I will be talking about CPU stack, so the one necessary for execution of your program on the CPU. It's supported in your instruction set. It's referenced in application binary interface, calling conventions, so on and so forth. It's universal. It's not only for C, no, C++. It's also used in other languages. What will be your takeaways? They will be threefold. For a start, you may come here just for entertainment and to enjoy the misery and torment of your peers. Maybe you're already working in Rust or some other so-called safe programming language. Then all what I'm going to show is no longer relevant to you. But it is very much relevant to us who still need to deal with C++ and the like. Second tier would be awareness. Awareness that there is entire universe under the hood, below what your compiler shows you, below your C++ or C code. And, well, it's at least worth being aware of the fact. And the third tier will be the comprehension. Perhaps you will learn it, perhaps you know it already, and you just want some reassurance. I will try to at least scratch the surface and show you what can go wrong, how can it go wrong, why it goes wrong, and eventually, I hope, how to fix it. Right, so let's start with the first chapter, the encounter. I want to share a story with you. The other day, I received a message from a colleague of mine, very experienced guy, who was dog fooding our product. Don't know if you know the term. Dog fooding means using your own product. It comes from the dog food production industry, where supposedly one of the founders of dog food company told that you need to eat your own dog food. So, meaning not taking it literally, but figuratively, you need to keep using your own product in order to make it better. So that's what my colleague was doing. He was having a set-top box at home, watching television at the comfort of his couch. And the other day, he approaches me saying that, hey, Bartosz, you know, this new streaming service that you've been integrating recently on our platform. I say, yes, what about it? It keeps crashing. All right, that's interesting because we've been testing it for a few weeks now, and I didn't notice anything special. So he continues, and he says that, yeah, it keeps crashing, but just when you watch live services. You can keep watching VOD on-demand content all day long. It works fine. But if you switch to live content, it sometimes crashes. All right, we've been testing it, we haven't noticed. Yeah, you know, but it only crashes roughly once a day, maybe once every couple of hours, every 4 hours or so. So if you keep watching live content all day long, perhaps you will observe 1 or 2 crashes. Okay, that makes it a little bit better, but not very much. So my colleague continues, and he says, yeah, there's just one final touch. It only crashes if you watch certain sports channels. Now, if I know something about sport, I'm not a big sport fan myself, but if I know something about sport, is that people get passionate about sport. When they watch their favorite athletes compete, they become passionate about it. So, probably half of you at least would follow some sort of football or volleyball or whatnot. Imagine yourself watching La Liga, wherever Robert Lewandowski plays now, in the middle of an action, and he's about to score, and in that instant, your application crashes. Does that matter that you can launch the application again and see the replay, time travel back, and see that goal? It doesn't matter anymore. It's gone. It's past. All your friends will be sending you messages on your social media. Hey, have you seen this? No, you haven't. You will in a moment, but you haven't. So, crashing live sports, if it's anything, it's a very bad customer experience. People are angry about it. So I knew instantly that I'm gonna have to do something about it. It's not gonna slip by. So, given that, since we already established what the problem was, my colleague, being an experienced engineer, managed to grab some core dumps for me, and it was very useful because I didn't need to reproduce it myself. The evidence was readily available. So I grab one of those core dumps and open it in a GDB, as any sane person would. Because that's on Linux, so GDB is your default debugger. So one thing that immediately stands out is the fact that they all come from a video stream thread. That's already significant, but it's not significant enough. On that slide, there's already something suspicious. I wonder if any one of you can see that. Sorry? Very well. Yes, it's unaligned, and it's suspicious. I mean, not that it's technically forbidden, but usually it's a sign of something going wrong. That's true. So I was smart enough with my years of experience to tell that, pthread mutex unlock, there's just no way it's going to be wrong. This is rock solid piece of software. It never goes wrong unless you pass invalid data into it, like this unaligned pointer. So I thought, it's worth looking at the parent function that called it, this do stuff, something. And yeah, so I opened the C++ code, and it looks roughly like this. It's a classic cliche. You log the mutex, you do the stuff in the critical section, and unlock the mutex in the end. And this function takes just one parameter, so this is an address to some sort of structure, and the structure looks roughly like this. It has some member, let's call it a pointer, doesn't really matter what it was, and at the offset there is a mutex. So right here, I would expect it to be at offset 8, because that was on a 64-bit architecture where pointers are of size 8 bytes. So address of the structure plus 8 equals address of this mutex. It's not guaranteed, but that's usually what it is. Yeah, so, well, I think there is nothing wrong in the code on the right side of the slide, is there? So I think, maybe it's under the hood. Maybe the compiler did something wrong. So I go to disassembly. Can you tell, by the way, by this disassembly, can you already tell what the architecture is here? That's right, it's ARM. It's specifically 64-bit ARM. Well, there is a reason why I want to torture you with this disassembly. I know it's not very eye-pleasing, but ARM matters, and it matters a lot. And another question to you, how many of you have something like that in your pocket? No kidding. Really? That few? I would think that some of you will have 2 cell phones already. Yeah, so most of the cell phones in the world, as well as a whole bunch of other devices, they run on ARM. And it's true for Android, it's true for iPhones as well. They may differ, so different ARM cores can be installed in, but it's usually ARM. I know that Android can also run on x86 and one other architecture that I forgot, but in practice, it's always ARM. So on ARM, there's one little thing that I want to tell you about ARM and the calling convention on ARM. ARM has 32 registers, and you know, to use the classic literature, all registers on ARM are equal, but some registers are more equal than the others. So the first 8 registers are used for passing arguments to the functions. So if your function takes one argument, it will be passed via x naught. If 2, it will be x naught plus x1, and so on and so forth. Additional beyond 8, that's a different story. Let's not worry with that right now. And there is a set of other 10 or so, yeah, 10 registers starting at x19. These are important because the ABI states that these values held in those registers must not change across sub-procedure called subfunction. So if you call some function, you are guaranteed that after returning from it, you get to keep the values in those registers. And there's the hero of our talk, of course, stack pointer, register x31, but usually it's just called SP. So let's take a quick few steps through the function here. I highlighted the relevant lines. So these 2 at the top and these two at the bottom are typical function called boilerplate, allocation of a stack frame, nothing interesting right here. Next thingy refers to what I've just mentioned, the contract of not changing x19 and x20. This function happens to want to use them, so it needs to store them somehow, somewhere. Here it happens on stack, because that's usually the easiest, and it's almost universally what the compilers would do. It's not required, but that's the easiest way, and it's supported by the hardware. And at the bottom, they are popped from the stack. Fair enough. So far, so good. Right here, we've got a calculation of some helper variables held in register x19. That's copied from x0, so the first parameter, the address of the structure. And in x20, we have x0 plus 8, so the offset of the mutex. So the address of the mutex is held in x20, while the address of this whole structure is held in x19. So far, so good. And then we proceed to calling the functions as specified in our C++ code. So moving from x20 back to x0 and calling pthread mutex log. This goes on very well. Then from x19 to x0 again, we call the subfunction which happens to take the same address as the function calling it. And at the end, we've got this dreaded pthread mutex unlock, which crashes. But why would it? I mean, you know, copying from the previously calculated x20 back to x0, it's guaranteed by the ABI. It should not change. But it did. So over here, everything was fine at the top, and the address was as it was expected. Down there, it's wrong. Why? It shouldn't change. Something must have happened in the function in between. Somehow it failed to satisfy the ABI contract. And if we look inside that child function, we see something that we already saw, a classic boilerplate, calling a function, stack frame disposal at the bottom. And in the middle, it pushes x19 and x20 to the stack again, because the child function itself wants to use them. So for a brief moment, x19 and x20 from the parent context happen to be on stack in the child context. That's crucial. So the issue is not in the function that crashes. I mean, there is nothing wrong with pthread mutex unlock, obviously. Similarly, there is nothing wrong with the parent function. The issue is somewhere here. The needle is in this haystack. And as you can imagine, this haystack can be thousands of or millions of lines of code long. And we need to find what happened. For a split moment, our registers were on the stack. After returning from do stuff logged, they were no more, or at least they got corrupted. How does it happen? Well, there is no magic. If you call the function, it allocates some data on the stack. That's classic. If it calls some other child function, the child function itself allocates some fragment of the stack memory for its purposes. And we go on, call some other functions. Eventually, we end up in a buggy function, which we need to find because we don't know which of those many functions it is. And this buggy function happens to write something outside of its stack frame, maybe here. And yes, of course, you can clearly see that this is out of bound right to an array, but we don't know where. And not just that. The buggy function itself will continue to run happily, unaffected entirely, and all the parent functions up to do stuff logged, they will keep running happily, no issues whatsoever, until we end up in do stuff log and then want to go back to mutex unlock again. So I guess many of you have heard about stack protector being a feature of the compiler that might help with that. But will it? The answer is on the slide already. It will not help right here. Why? Because that's what stack protector does. It pushes merely pushes one integer value to the stack prior to calling a subfunction and checks it back upon return. So these extra variables pushed to stack are sometimes called sentinels or guards or canaries. After canaries, the little yellow birds that used to be used in mining industry to detect presence of lethal gases in the underground chambers. And you put the canary into a chamber. If it survives, it's safe for the miners to go in. If it dies, tough luck for the bird, but at least it's sacrificed help to save some people's life. So if the buggy function happens to corrupt its own canary, it's detected pretty much immediately, already upon return from the buggy function. That's okay. It's already deferred a bit, but not very much. If the buggy function overrides a parent canary, well, it's a bit worse, but still not dramatic. The worst case is if the buggy function corrupts something else. It's not detected by canaries at all. So the execution continues, and as in real life, if you're young and make a mistake, you may not necessarily realize it instantly. You may be haunted by that after many years. So similarities between life and computer programming. A buggy function does something wrong. Do stuff the parent one suffers. So one might ask a question, a very legitimate one. So what's the stack protector good for at all? And it is good, and it's designed for saving you from contiguous stuff overrides of memory, not just, in this case, stack. Yes. So if you go off by many bytes, there is a very high chance of you corrupting at least one canary or many canaries in a sequence. But not if you, I'm going back one step, not if you do that. Sorry, that's just not the right tool for the job. So since I already told you what the issue was, the question remains how to fix it. Because we've got this huge haystack, and we need to find a single needle inside it somewhere. But how? Does any of you have an idea, or maybe know a tool that might help in such a situation? We could, but in my practice, yes. Sorry, just to say it loud to the microphone. Can we set up the right trap? Yes, we could, but we don't know what address specifically will be written to. So that's the one challenge with this approach. Yes, but still, stack is 8 megabytes long. In this case, yes. In this case, yes. But the layout of the stack, I mean, it's simplified on the slides, but in fact, it was written to a different address every time. So, to an extent, we could use mprotect to guard the entire areas, entire pages of memory. Okay, that's an interesting approach. It could work sometimes, not always. Any other guesses? Memory sanitizer. Okay, does it apply to stack? I think it does. Okay. I didn't know that. Interesting. Okay, we'll have to check that. Thank you. There we go. Thank you. Yes, I was hoping for that answer, and the answer is unfortunately not, because it was happening in a web browser process, and as you can imagine, web browser is quite a heavy process. So it just couldn't handle the overload. But yes, I'm a big fan. Valgrind saved my day multiple times. So yeah, I would think, yeah, let's do it this way. Can't, not this time. So I was chatting with a friend of mine who happened to be working on my team back in the day. He's sitting over there. Adam, shy, raise your hands. And you know, I was doing some brainstorming and said, hey, we've got this concept of stack protector. It's powerful. We could leverage that. can we perhaps modify the compiler such that instead of pushing canaries, like a simple data onto the stack, perhaps it could call our function and then we make the whatever is necessary, verify that the stack is still correct, and just return the value. It's good or no, it's not, and then just crash. And as you can imagine, that's a really challenging idea. And Adam, being himself, he doesn't take impossible for an answer. He said something along that, I think I might have an idea how to do it in just C/C++ without descending into compiler. Maybe it was something along that line. So yeah, with that, let me present you the shadow stack. Before explaining how and what it does exactly, I will first tell you where the name came from. It was inspired by the concept popular in politics, at least in British politics, as far as I can tell, the concept of shadow cabinet. So imagine that in some country there are two political parties. They are called big endians and little endians. These names are relevant. You can check the reference down there. So imagine the big endians have just won the election. They got the majority in the parliament. They get to appoint the government, the prime minister, and the number of ministers, however many there are. Maybe they are called secretaries in other parts of the world, and then there is no prime minister, irrelevant. What does the opposition do? They will appoint their own set of ministers and prime ministers. And don't get me wrong, they have no administrative power whatsoever. They are just shadowing what the actual government does, proposing alternative solutions, criticizing the main government. That's what politics do. Such that in an unlikely event of a turnover, suppose some of the members of the ruling party happen to be convinced to switch sides, the opposition instantly have a set of people waiting on standby that can take over the new roles instantly from day one. Or perhaps in IT we would say from the 0 day. And that's exactly what the shadow stack does as well. It copies the actual stack and makes sure that it stays in sync. The shadow copy stays in sync with the actual stack. In pseudocode it looks roughly like that. First, before descending into a sub-function call, just take the current stack pointer and copy the missing area into the shadow area. So copy from the actual one to the shadow area and move on. Continue with descending into a sub-function. Just after returning from the sub-function, do the opposite, right? Drop whatever was necessary. And in between, twice, just before descending and just after return, compare the shadow area with the actual area. If there is an issue, if there's a mismatch, then do whatever is necessary. In action, it looks like this. We've got the doStuff function, and it has some data on the stack here. Before descending into sub-function, we copy it to a shadow area. Then we compare both. Right now, it doesn't make much sense, maybe, but in a second it will. And as long as there is no mismatch, memcopy says it's all equal, we can proceed to a child function. And it will have some data on the stack. We've seen it already. So maybe it itself wants to call another sub-function. So again, the shadow stack kicks in and copies it to the shadow area. And then compares. Maybe it's already wrong, so we will report about the execution. So far, it's OK. And it calls another function. Same story again. Copy to the shadow area. Compare. Descend into a buggy function. Finally, we arrived at the buggy one. And we know it already very well. It corrupts the stack. So far, nothing is detected. The execution continues. But when the buggy function itself calls another sub-function, or perhaps when it returns, right here it returns, shadow stack kicks in, and upon return, it compares the memory, and it detects a mismatch. What do you think should happen right now? Crash. Good idea. Or fix. Good idea. Or maybe nothing. Of course, we've got a correct copy. We can fix it. And continue execution happily. Is that good approach? Sometimes it might make sense, of course. If you are prepared to pay for the overhead of shadow stack, which is maybe not very huge, but it's substantial. It's n squared, obviously, because the more you descend, the more data you need to compare at every single descent and return, so it's n squared. It's not good. Sometimes it may be too much. But generally, healing it's like sweeping under the carpet, it's pretending it never happened. But maybe it's reasonable to gather more evidence. For instance, you have 2 cases of corruption, so maybe you want to find them both in one go. The alternative, of course, was mentioned. We can just dump the report to the standard output or wherever it can go and crash. And there's a huge difference between crashing here and crashing over there. Over there is far away from the corruption. Right here is very close to the corruption point. So it's just easier to look at the code and see where it crashed. Where was the problem? The implementation looks like that. In C++, it's pretty simple. We use std invoke, and we wrap it in our invoke. And we add a bit of magic here in between. All the comparison and what I showed you on the previous slide. In C, it's cryptic. It requires some preprocessor magic and some compiler extensions. And little did I know that in C you can do something like perfect forwarding, although it's far from perfect in C, but it's doable. I don't know if I would ship it into production, but for the purpose of debugging, maybe it's worth it. And usage in C is pretty simple. You just wrap whatever function call you are suspecting into our macro and run the program again. In C++, it's even easier. If you've ever used std invoke, it's the same syntax. So you wrap your function, you take the function pointer, and call it with the object or whatever parameter it requires. It also works with pointers to methods, although the syntax is a little bit more cryptic, as is always the case. You may need some casting in order to choose the correct method. You can imagine all of that: virtual methods, overloaded methods, const methods, all that stuff. It's supported, it works. Maybe you don't have the luxury or don't want to bother with introspecting your code, with making the changes. We've got you covered. You can use LD preload, why not? So without recompiling your broken binary, you can write a preloadable library that will just wrap the actual functions and do the magic under the hood. It also works with C++, but you need to know the mangled names. Yep, that's it in a nutshell. Now keep your fingers crossed, please, for me, because I'm about to show you it in action. There we go. Right here, a bit of a spoiler. And where's my scenario? Here it comes. Here it comes. Here's my scenario. So I've got a binary which is broken or can be made broken. Can I just mark it? Yes, I can. I will just run it the usual way. Where is this, my shift key? It just runs, nothing interesting happens. Then I can make it corrupt the stack at the offset of my choosing. Here it's offset 140. And it crashes, expectedly, because it's a demo application. We may want to, how do I do it? Like that. We may want to look at it in GDB. Why not? There we go. Let's run it. And we've got a segmentation fall, just as expected. And if we look at the backtrace, it's what I showed on the previous slide. so far, nothing surprising. I've got an instrumented version of that library, which will differ by the offset, and it now uses our shadow stack concept. There we go. Or maybe it's make it a bit smaller. There we go, such that it fits on the screen. I don't want you to look at all of this, of course, but that's the shadow stack report. Is it large enough? Can you see it all? Okay, thanks. Yeah, so after return from the buggy function, shadow stack notice that there is a mismatch between actual stack and the shadow stack. On the left side there is original being the runtime stack, which got corrupted, and on the right side there is a shadow stack, which is the pristine copy. And in this line, as you can see, the familiar 03 was written over here, whereas there should be AA. All right. So, well, at least we know that which function is suspected. And obviously we can run it as well in GDB. The same thingy. Run it. And now we've got abort, because that's what we wanted. We want to force abort. And when I showed backtrace, now we know something more. Maybe I'll make it a bit larger. Now we know that we managed to get into the other function, and from the report from the shadow stack we know that it was after the return from the buggy function. If I list the code, can I? Oh no, sorry, I need to switch to frame 7 and list the code. So we know that after returning from the buggy function, something was wrong. There are several options. If you have perhaps fewer screen state, then you can adjust it. Oh no, sorry, not in GDB. Right here. So you can hide the equal lines. Of course, you can just show one part of the screen, just left versus just right, whatever you please. You can make the lines shorter, say 8 bytes per line, not 16, as is the default, usual stuff. And oh yeah, this one is interesting. You can try to heal this thingy. There we go. Can you see the stack fault? No, because it's missing. And there's an option, quiet heal. So don't report anything, just heal heal your stack. And everything is happy, yeah? Sunny day. And the last thing is the preload. So without modifying the original binary, let me scroll upwards. Over here, yeah, there is my preload kicking in, doing the stuff, without changing the binary itself. Now I will switch back to the slides, like so. Off to the summary. So I owe you the closure. Have we managed to find this bug that was haunting us in the first place? Yes, we have. Otherwise, I wouldn't be standing here bragging about it. It was an issue in one of the libraries that we use. It's called GStreamer. If you are into multimedia processing, you will know that library, very respectful library, reputable. And just so happened that in one of the lesser used functions, it was missing data inputs, input data sanitization. It was writing at offset 240 into an array of size 10, obviously wrong. And it had been fixed a few months earlier before we noticed that error. So we simply cherry-picked the fix from the upstream. On the shadow stack itself, is it mature? No, of course it's not. It's just a proof of concept. It's not a free fish. It's not even a free rod. It's a blueprint for a rod that you can make yourself. But we've got one example rod available. So you can kickstart with that. Main lessons for us. Stack protector should be used consciously. It's not an almighty savior. You need to know what it's doing and how it's doing in order to apply it for the specific issue. It's good to check your dependencies every now and then. Maybe the bugs that you are fighting with are already fixed upstream. This has paid off more than once for me. And the finally, the order matters, and it's not just the order in society, although that matters as well. It's the order of the stack. So imagine what would happen if the stack was growing from the other direction, from lower memory addresses towards higher memory addresses. You start here, let's say at the beginning, at 0 into the segment. You call the functions. You end up in a buggy function eventually. And it corrupts something. What does it corrupt? Free space. No worries. Don't get me wrong, it's still a buggy code. You should avoid it, you should fix it, but at least you don't get to shoot yourself in the foot in the process. Does it mean we can switch the order of the stack? As far as I know, there are systems out there that do just this by design. However, they are in minority. Most of the systems out there, they will use the regular. If you the order of the stack that you are all familiar with. So can we switch the order of the stack? I will leave you with that question. Please answer it for yourself. Now I'm happy to take a couple of questions from you.
Big round of applause to Bartosz. Thank you very much for this interesting mystery case. And now we'll go with the question, of course. So, and the questions already. Please raise your hand. So first question I can see here.
Oh yes. Do you know any way to use it, this LD preload method on Windows ecosystem?
Awesome question. No, I don't know. It doesn't mean that it doesn't exist. It just means that I'm not experienced with Windows, so I won't speak for Windows part of the world. As far as I can tell, the Windows loading system, the libraries on Windows, they have different semantics. In Linux, all symbols by default are wrappable. On Windows, by default, they are not. So, well, on Windows, they need to be made explicitly or wrappable or overloadable, if you speak.
All right, thank you. Second question I saw here.
I'm gonna branch out a little bit because here we have a stack at least, but what about issues where we have a program that silently corrupts memory somewhere and the behavior goes out of the window? And you know, you could use debugger, you could use silly prints, and you have third-party libraries there, and you have no idea where to start. Where would you start? Like, what would be the tool of your choosing?
Awesome. You mean like corrupt the heap instead of stack?
Yeah. Yeah.
So yes, I did have to address an issues like that at least twice in my career. So it's often improvising, but I recall specifically one issue with custom-made memory allocator, and to our demise, it was an allocator which was using in-band metadata. So just before the memory that got returned to the caller who wanted something, there was like a header just adjacent to the actual data. So that's called in-band metadata. It's a big no-no. I discourage such design, absolutely, but that's what it was. And what did I do? I think, it was a crude approach. I made all the ifs in the entire stack to just do the extra check for me. So instrumenting the if, we turned it into capital if, and it was doing the actual thing, but just beforehand it was checking, hey, this address, is it broken already? And then when it detected it got broken, luckily for me, it was the constant address, so where I know where. So speaking to this idea of having how it's called, the debugger thingy, the trap, the hardware trap. So that couldn't be used on that system, but instead I turned all the ifs into a checker. Would I recommend it like a standard practice? Probably not, but it paid off.
Thank you very much.
Okay, thank you. Another question here, and then we'll move back to that part of the room.
Hello. Wouldn't it be cool to have this implemented as a, let's say, opt-in kernel facility? So you could run without recompilation, just opt in on a kernel level for these checks and maybe even healing?
You mean to protect the kernel itself or to protect the user space application?
To protect the user space application from kernel.
it wouldn't be so deterministic because to an extent you could do it upon the context switch in the kernel. So if the application is swapped out or maybe swapped in again, you could do this check and yep, I can see, I mean, it could be feasible, not with the current state of our code, of course. It wouldn't be deterministic, not so much. So maybe the takeaway would be smaller.
Okay, I see. Thanks.
All right, thank you. I saw a hand here in the middle and then one back. And let's take those two questions still.
Hey, from what I gathered from your issue, you have to decorate every call down the call tree to try to isolate the issue. Does that mean that you basically had to add a few, then reproduce the bug, then try to narrow it down again and again? Like, how long did that take?
Yes, that's roughly what it took, and actually can show you that in the code. So I should have a diff here, maybe here, right? So that's the original on the right and the instrumented thingy on the left. And yes, basically that's what it took. We had to instrument every call that we suspected. Luckily, it was only on a single thread, so there was just a subset of those, maybe 100 or so. Yeah, that's what it took. How long did it take us to reproduce? I think around a week or so. I mean, we were reproducing it more often, the issue, but the fact that it was reproducing only once a day or maybe twice a day, yes, it got an impact. So we rather took the approach of instrumenting more than necessary in the hope that we will get something in return faster.
All right, thank you. And there was one more question in the back.
There's a gentleman desperately wanting to ask question.
In a black t-shirt,
yeah,
as I can see. The black one.
Yeah.
Black.
There you go. There you have your chance.
Yeah, so I couldn't quite catch that, but my question is, how do you protect against like legitimate stack modification by another function? Because it looks like you're kind of detecting if someone modified my stack, but if I like
yes,
allocated a pointer for someone to use or kind of buffer,
yes,
how do you protect against that?
We don't currently. However, yeah, I did anticipate that question. Thank you for asking that. And we do have an idea how to implement it. We call it so-called ignore zones. This could be easily implemented. And if I know Adam well, and I think I know him well enough, he might be able to implement it by the end of this week. So
right,
it's an easy thing. You just keep track of the zones that you want to ignore, and before making the comparison, you just copy that zone from the actual stack to the shadow area because you don't care, and
sure,
then you just perform the very same memory comparison across entire area.
Yeah, but I would have to sanitize every buffer myself, right?
Yes, you would.
Okay.
I mean, we didn't introspect the code. We didn't do any meta introspection or anything like that. You need to specify that, hey, this is the area that is supposed to be changed by the callee.
All right. Since you mentioned writing a plugin for a GCC, maybe it's simpler to just run Valgrind, but on a subset of the program. Like you don't have to instrument all of the buffers. You can like instrument a small subset.
Yes, if you can narrow down the problem, absolutely, by all means.
Yeah.
Yeah. So
also, but most of the features, I think the sanitizer will cover. It will do some kind of like, because if you have like a specific type, like you have a pointer to a type, you kind of know how big it is. So you know when you have a wrong access, like like a corruption. The only problem is with arrays, and then you kind of instrument every array access with a bounce check. If you don't already use like std array or other container.
Yep.
So I think you maybe want to go in that direction instead. But yeah, it's just a suggestion.
Good idea.
Thanks.
Speaking of what? Oh yeah, the sanitizer. There was a question earlier about how to approach heap corruption. Sanitizer are a good idea. Yes.
Yeah, heap corruption is great. For stack, I'm not sure if shadow memory works. I think it does by instrumenting the arrays accesses. It may not work in some edge cases on the stack. That is true, but yeah. I guess you can get
That's absolutely good idea.
Yeah, the results with types plus sanitizer, like a type system instrumentation and sanitizer, I think.
Sure.
And it's more like a portable and
All right, thank you very much for all of the questions. And once again, big round of applause to Bartosz.
Thank you very much.